Hello, I'm Phil Yaskin from Texas A&M University. I'm currently writing a calculus textbook called MYMathApps Calculus. It's a commercial, self-published textbook, and it's available for purchase at MYMathApps.com, but a sample can be seen at this website, which I'm going to go to soon. The book contains lots of graphics made with Maple, both 2D and 3D, both static and animated. Today, I'm going to share with you some aspects of the book and with emphasis on the plots. Whenever possible, I will use the sample version so that afterwards you can go there and look for it yourself. Okay, so here is the textbook. It's broken up into Calc 1, 2, and 3. When I first started writing the textbook, I started with Calc 3, then Calc 2, and then Calc 1, primarily because I felt Calc 3 and Calc 2 was where you most needed to have 3D visualization. And also because I did not like the treatment of Calc 3 in Stewart's textbook, which is what we were using here at A&M. We still are for most of our classes, except from some pilot classes using my book. In many of the chapters, there are exercises, and then at the end of each chapter, there are exercise pages. So for example, here's the exercise page on related rates. Every problem has an answer which drops down and a solution hidden behind a button, so that students hopefully will do the problem first, check it against the answer. If they don't get it right, they can try again, and eventually, if they need to, they can read the solution. Some problems also have a hint, but as you notice, there are lots of pictures on these pages describing things. I believe that this animation is one of those that are being submitted for the Maple Animation Contest. It was made by one of my middle school students at my summer program and then improved to include in the book as a related rates problem. I'm going to start with Calc 3. And so here is the table of contents for Calc 3. It's broken up into 4 parts: geometry and vectors, dot products, cross products, properties of curves, line integrals, then derivatives, limits, partial derivatives, chain rule, directional derivatives, max-min problems, divergence and curl and potentials, then integration, first in Riemann sums, and then rectangular coordinates, followed by curvilinear coordinates, such as polar, cylindrical, spherical, and eventually general curvilinear coordinates. After that comes parametric surfaces and surface integrals. Finally, the 4th part of the book is the 4 theorems of vector calculus: fundamental theorem of calculus, Green's theorem, Stokes' theorem, and Gauss's theorem. Okay, so let's start with the coordinate systems. So there we learn about polar coordinates and how to plot polar curves. And there are things like how to plot a cardioid. All of these pictures were made with Maple. The animation at the end shows them how to actually draw it with their pen. It was exported from Maple as a GIF, an animated GIF, and then converted into an MP4 so that you could stop it and drag it. It can be used as a lecture demonstration in class. Not only do we have cardioid, we've got limicon, we've got roses, and we've got bigger roses. Then we've got cylindrical and spherical coordinates. So here is spherical coordinates. I've got a plot of the general surfaces, and then lots of plots trying to get the students to understand what a constant surface is and what a coordinate curve is. Applications. We frequently, applications such as work, have animations in here. Here, a girl is pulling a wagon down the road. This is for dot product. And so the animation is not crucial to doing the problem, but it gives the students more of a feeling for what's going on. Then we come to cross product. Here is trying to understand cross products. It's difficult for the students to visualize the right-hand rule and cross products. So here they're being shown how three vectors can form a right-handed triplet, a left-handed triplet, or be coplanar, and how you determine that by looking at the sign of the triple product. Also have a complete catalog of quadratic surfaces, and more on the next page, which are the paraboloids and cylinders. Then when they get to studying arc length, it's important for them to understand where the formula comes from by chopping up the curve into little line segments, computing the approximation along the line segments, and seeing the number of line segments gradually increasing. Again, you can stop it and step through the creation of the Riemann sum. Properties of curves, visualizing how curves are drawn parametrically. Here is the twisted cubic. If you look at it along two of the coordinate planes, you see a quadratic or a cubic. However, when you look at it as a 3D plot, you see that it is a curly curve called a twisted cubic. One of the things the students need to learn about is why the tangent vector is in fact the velocity vector. And so right here is an animation showing the proof that the secant vector approaches the tangent vector. Later, students need to learn about torsion. And so the torsion is what determines whether a curve has a left-handed or a right-handed curl to it. And you can also see that by looking at the tangent, normal, and binormal vectors for this helix, for example. Linear approximation. Here is a one-dimensional linear approximation. And so you can see that the function approaches the tangent line approximation before both of them approach the actual value of the function. So they coalesce just about right now. Okay, we have a similar thing for plots in two variables. So the function approaches the tangent approximation now, and then both of them approach the function value. In studying properties of gradients, the students need to understand the main properties. And so there are graphics to help them understand why the gradient is the direction of maximum increase of the function. And there are animations which help them see that the gradient is supposed to be perpendicular to each level set, both in 2 dimensions and 3 dimensions. Notice the gradient is not drawn perpendicular because you shouldn't assume what you're trying to prove before you've proved it. So I draw it not perpendicular, but then the algebra proves it must have been perpendicular in the first place. So now we need to understand Riemann sums when we get to integration. Here are pictures showing a 2-dimensional Riemann sum animated with more and more rectangles. Once again, you can pause it as a lecture demonstration and gradually show the increasing number of rectangles. In trying to understand general curvilinear coordinates, people need lots of visualization. So here are a bunch of coordinate systems These are standard maple plots. Understanding how you construct a coordinate grid and how you compute the area and integral using curvilinear coordinates. One notable feature in Calc 3 is that I treat line integrals at the end of chapter 9, at the end of the first part. I treat surface integrals here at the end of the third part, and then the fourth part includes Green's theorem and Stokes' theorem. Students find it very confusing when you get to those theorems because they say that sometimes you can use a line integral to compute a surface integral, and sometimes you can use a surface integral to compute a line integral. If they have just learned about line integrals and surface integrals, which is common in many calculus books, then they haven't had a chance to absorb them. By separating line integrals and surface integrals and treating them in their own right first, before you get to theorems, students have a chance to integrate those concepts before they get to dealing with the theorems. And then when you get to Stokes' theorem, one of the hardest things for students to do is visualize the boundary. And so here are animations which show where you put your thumb and how you go around the boundary. Okay, again, how you use the right-hand rule to determine going around the boundary. It becomes even more complicated when there is a hole. And then you have to go around this way, clockwise on the inner boundary, counterclockwise on an outer boundary. Here, there's no inner and outer. You still need to know which way to go around. So that finishes Calc 3. Let's go on to Calc 2. Here is the table of contents for Calc 2. First, they learn techniques of integration, starting off with antiderivatives and Riemann sums, and then the various techniques of integration. Except on antiderivatives and Riemann sums, there aren't many animation in this part. Then we come to applications of integration: area, average value, mass, center of mass, arc length, surface area, volume, work, and fluid force, and polar coordinates. There are many animations. Then there is a introduction to differential equations as an application of integration, followed by sequences and series. Let's take a look at the animations. Here is the standard animation for Riemann sums. Break the region up into intervals, draw Riemann sum rectangles, and do it with more and more rectangles, and approximately you get the area under the curve. The fundamental theorem of calculus is proved using animations. And so the area function, or better, the integral function, since it might not be positive, is the integral up to a certain point. And what we'd like to know is what is the derivative of that function, because that's the first fundamental theorem of calculus. The proof is hidden in a button because not every student wants to read it in all its detail. Here it is for those who want to go into that detail, or a faculty member who wants to teach it. Applications. Here is mass and center of mass. This is the exercise page. And so you have a lot of bars with varying density. They're done using Maple's density plot. You have a discrete situation where you need to find the center of mass, followed by a bar center of mass and a moment of inertia, electric charge, etc. Volume. Here's the exercise page. There's one where there's a remark, and it says when the cross sections over a disk happen to be semicircles, the resulting volume is a hemisphere. And the remark is simply telling them that it is quicker for them to have computed the volume of a hemisphere instead of doing the integration. Or they can use that to check their work. You'll notice that the solutions have a base surface, a slice, and accumulated slices. So that's for volumes by slicing. Then we've got volumes by thin disks. We have one Riemann sum slice rotated and then accumulating the slices. Then we have thin cylinders. So you have a cylinder rotated and accumulated to produce the volume. Here we have washers. Again, a slice is rotated and then accumulated to produce the solid. On geometric series, there are problems. Some of them have a picture in the solution for students to look at because offhand they ought to be able to figure it out themselves. There it is in the hint. And then here's one, it's in the problem because I feel the students need the help of the picture in order to understand the problem statement. Then we come to Taylor approximation. Here is the Taylor series and its graph for various numbers of terms all the way out to 15, and the students get to see how good of an approximation the Taylor series produces. That finishes Calc 2. On to Calc 1. Here is the table of contents. There are things reviewing pre-calculus. Then we come to limits and continuity, intuitive, computation, applications, and the precise limits. Then we have derivatives, differentials, chain rule, inverse functions, higher derivatives. Applications include parametric curves, limit by L'Hopital's rule, solving equations using Newton's method, related rates, how to do graphing, and max-min problems. Then we come to integration, which is an introduction and is repeated again in Calc 3. So what do we have in plots? On limits, there are lots of plots helping the students understand limits from the left, limits from the right, and the value of the function. And when the two limits are equal, we get a two-sided limit. The function value may or may not exist, and it may oscillate. There are quizzes trying to get them to understand these in detail, followed by understanding two-sided limits and one-sided continuity and two-sided continuity. Also in limits, we've got the sandwich theorem and the theorem specifically for sine and cosine, the intermediate value theorem, the extreme value theorem, the mean value theorem. There you'll see the plots in the proof, which starts with Rolle's theorem. When you look in the exercise page for the theorem, in the checks, the fact that the graph has the tangent lines having the same slope as the line between the endpoints. Then there is the standard animation, which shows why the slope between the secant lines has a limit, which is the slope of the tangent line. After knowing about the derivative, students need to do linear approximations. This is the same animation that was used in Calc 3 here in Calc 1. Graphics also help students learn inverse function. If B is f of A, then A is the inverse function of B. The plot helps them realize that that is the mirror image through the 45-degree line. Then by drawing rise, run, slopes, they can see that the slope of the inverse function is the reciprocal of the slope of the original function, which leads to the inverse function theorem, which is also re-derived using the algebraic technique. But the geometrical pictures help many students be able to visualize the theorem. Then we come to the inverse functions for sine and cosine, tangent, secant, cotangent, and cosecant. The chapter on related rates has many beautiful animations. Then there are some on the exercise pages. So that concludes Calc 1. In the question and answer period, I will answer your question. Thank you for listening.